Oh, maybe it doesn't have it. Oh, here it is.
Oh.
One sec. Right. Yeah, I don't know. It might be. I don't know if it recognizes. Sometimes it works, sometimes it doesn't. Huh?
Should I change maybe? Is this is the USB, right? So,
What?
oh.
But you don't have your slides.
Yeah, maybe.
Read them out.
Oh, yeah. Shit, fucking hell. But then I cannot.
So it's already the start of your presentation.
Yeah.
Okay. Then it should work. So I don't know why.
Should I just use my mouse?
Maybe you can mute yourself first.
Yeah.
Yeah, mouse is fine. So
Yeah.
this one should. But you can use it as a pointer. You don't need to. Pointer works independently.
Okay. Yeah.
It's just for the slide changes. You need that connection, but it doesn't work. It seems.
I will try again for yeah. Oh, yeah. Come on.
Let's overshoot by 1 or 2 minutes. I see some master students. Maybe they will
Yeah.
come here. Good morning, everyone. Happy to see so many happy faces here. Welcome to the IvS seminar. So today's speaker is Dwaipayan. He's a PhD student with us. He did his bachelor in India, has a engineering bachelor, I believe, and master's in A&A also here in Leuven. So if you have master students in the audience here, keep in mind. Okay. So Dwaipayan is going to talk about the multi-D, and I spied already on him a little bit, so it's going to be a 2D plus 1D dimensional unified atmosphere and wind simulations of all stars. So we go very massive today. Okay, the floor is yours, Dwaipayan.
Okay. Yeah. Am I audible, right? Yeah. Okay. So welcome, everyone. So today I'll be talking about our new multi-D simulations of O-type stars. Well, inspired by last week's presentation, I think it's a better way to name them, 2 plus 1D, since we are going 2 spatial dimensions and 1 time dimension. Speaking of O stars, they are massive stars, and since there is a lot of master students here, maybe it's also before that. There's a tiny bit of joke. So Nico said, we're all standing on, not originally, but he said last week, that we are, standing on the shoulder of giants. And, in our case, the giants are all these people over here, right? You might recognize some of them. Go ahead. So moving ahead, so massive stars, right? So this is like a brief idea of how they evolve over time, and they end up as this kind of compact objects. Can be black hole, can be neutron star, depending on how much mass they end up with. But this is just a simple, way, this single star evolution. But then this situation is complicated if you add certain other phenomena, such as feedback. So what feedback in massive stars, what they can do is that they can enrich your interstellar medium with, with fusion stuffs that they, form. They can also provide ionizing radiation and thus hinder star formation. And one way that massive stars do this kind of thing is through their outflows. And a way to look at outflows would be through the so-called classical Eddington factor, which is nothing but the ratio of your radiation force by your gravitational force. And what do I what is this radiation force? Well, I just want to point out that it's proportional to the opacity of the medium. In a more classical sense, as I mentioned, classical Eddington ratio, what it means is that the opacity is only electron scattering. And if you plug in some rough numbers here, you get values for sun, which are of the order of 10 to the power -6, whereas for these massive stars, it can be as high as 0.3. So what do I mean by that? Well, a little push can actually cause an outflow. I'll come back to that later. What is that little push? But for now on, let's move on, and let's see a bit about the sun. Let's play a little quiz. So, okay. Which one do you think is a model of the solar surface? People who think it's the left one, please raise your hand. People who think it's the right one. So you think the right one is the model? Well, it's kind of an even spread, but the model is actually the left one. So the thing that I wanted to actually emphasize is that these solar surface models are really amazing. Like they can actually seem even, like, resolution-wise, they're even better than what we observe. If you want to model the solar surface, well, you don't really have to, model the wind. If you're not modeling the wind as per. But what do I mean by that? Well, in case of these cool stars, you have your, if you have your classical photosphere, solar community, they call it the tau 1. We call it the tau 2/3 point. But then the wind is actually launched much, away from the surface of the star. But what happens in hot stars is that you drive the wind basically from or really close to the photosphere, actually sometimes even below the photosphere. In evolved Wolf-Rayet stars, as for example, you start blowing the wind below the classical tau 2/3 photosphere. So the problem is with this is that when you model this sort of wind plus atmosphere models of your massive stars, you need to do that in an unified approach. Yeah? So you model both the atmosphere and the wind. And this makes things more complicated. And it has been done. Like, for past 40, 50 years. But most of it has been done in 1D. Here are some of these 1D, really highly developed 1D massive star wind plus atmospheric codes. But then, if 1D has an issue, so the issue is that in addition to the mass of your star, the luminosity, the radius, metallicity, rotation, you also have these other parameters that you actually need to provide. But in case of multi-D, we actually derive all these parameters from first principle, basically. So moving ahead, so hasn't it been done in multi-D? Well, yeah, it has been. The Athena++ group in the US, they have their really beautiful simulations of their massive stars. But there's an issue. They don't have any wind. So it's not a unified approach. What are the problems with this? So you have classically a radiative envelope, but then you have these turbulent layers as well. We suspect from, well, we don't know yet in this presentation, but suspect them from the iron opacity peak, and also you have your outflow. So this is a whole bunch of things that goes on. So it has been done, well, in our group by one of the giants that you have seen before. Nico has done it for the Wolf-Rayet stars. But now let's move back to the O stars. So this is one of the simulations of our O stars. Well, what do the colors here represent? So this is a zoomed in part of this big panel. So yeah, and this line here is your photosphere. What the colors here are actually just relative density. So that means the purple parts are high density regions, whereas the green parts are low density regions. But that's this detail I will come back later on. But what I want to emphasize right now is that, again, if you look at the in this part of the figure, see this quasi-stable envelope of the star. Then you have the turbulent atmosphere. Then you have your photosphere, or R 2/3, and then you have your outflowing part. What if I look at what kind of temperatures they are? So 400,000, 150,000, 40,000, 20. So it's the problem is it's a fast regime that we need to cover, and a lot of things, different things that is happening. So what can we? What other challenges, or what we want to answer from the observational side of things? Well, when you fit 1D spectra, you need to add this ad hoc broadening terms to actually fit the observed spectra. We believe that multi-D simulations can solve this issue potentially. Well, let's just see. Also, it can have an effect on the derivation of chemical abundances, log G, which leads to this so-called mass discrepancy that is seen in evolved stars. So, as I mentioned, I will come back to this opacity. So, classically, as I mentioned, it's the electron scattering opacity, right? But, well, this is not the only opacity source. So, what else do we have? We have the Rosalind mean opacity, which is basically an average of. But it's one thing that I want to mention is in static. It's in static media, right? So and we actually use the opal tables by Roger and Iglesias from '96, and then okay. So maybe I'll just describe a little bit what you are seeing in this plot. So this is your radius, but it's modified a little bit. So what we're doing here is that 0 is your photosphere. Huh? So and also anytime you see this red line, any scaling, this is your photosphere, tau 2/3. This is your opacity. So and when you plot these opal opacities, you see this peak here. And this peak is called the iron opacity peak. So it's because of iron, these higher ionization stages of iron recombine at around 200,000, 150,000 kilokelvin, Kelvin. And this gives rise to this peak in opacity. You also have the helium opacity, the hydrogen opacity as well, but it's not that prominent actually in this figure to notice. But yeah, they're there. So what is opacity? So basically, think about the photon coming in from the star, and it interacts with your line, and then it pushes. It supplies a little bit of momentum to your atom, and this gives the atom a little push, right? So this is what I mean, by having an opacity, right? But imagine there's like several of these atoms, and they will all interact, right? But this is already covered in your opal tables. But in these massive stars, there's something else that happens. These atoms, they move at different velocities. And we all remember from our bachelor classes, right, that when the things move at velocities, they experience Doppler shift. So they might see the photon redshifted, right? So when you have Doppler shift, this same transition can interact with different photons in the outflow, right? So it's not about one push. It's you keep on pushing. And this, keeping on pushing. This actually it has been. We knew about this from CAK theory from how many years? 50 years back. And this push actually causes keeping on pushing actually causes an enhancement of these line opacities. On top of that, you have several thousands and millions of spectral lines. Here, this is just one ionization stage of iron, and then you have like several of these ionization stages of several of these elements. And, the resultant is a lot of force. And this is this dynamic line opacity. Together with the Rosalind mean opacity, is all in the hybrid opacity model by the second giant, Luca, from our group. So this is the opacity that we put in our in our simulations. So also, since it's a 2D simulation, right? So it's a 2D simulation, right? So we need to provide it with some initial conditions. So the initial condition is basically nothing but a 1D radiative envelope and then an analytical wind on top. So what Cassandra does on top of that is she perturbs around this unstable regions, and you put some sort of little seed for structure to form. Well, the mathematics of that is really complicated, and I believe that she's working on a paper. But for me, as Andre already mentioned, that I'm an engineer, and I believe that G is 10. So for me, this mathematics is way too complicated, right? So and then we put it in our in our grid, and then we copy it, and then we let it run. So okay, time for a breather. So let's see some of the results that we have obtained. So now, as I talked about, right, the gamma, which was the electron scattering gamma, but again, then I mentioned the two other opacities. They also have their own gamma, right? So you have the gamma opal and the gamma CAK. So together is the total gamma, or here it's just gamma. So if you remember, you saw that bump in your iron opacity peak, right? And if you notice here in this, so what these are actually time snapshots of our simulation. So different times. So if you remember, there was a peak below the surface of your star, and this is this, you see this peak. So this is the iron opacity peak. Actually, you can see from this plot. It reduces, and then line driving takes over at some point, and you just blow everything out. So what happens to the other parameters? Well, from top to bottom, you have your relative radiation temperature, you have your relative density, density contrast, and then you have your radial velocity. So if you want really a niche thing, you might notice that you see that when you hit your iron opacity bump, and you see this contrast. Below that, everything is close to the mean. As soon as you hit your opacity bump, things starts happening. Interesting. So you see it's high and low temperature regions that are being formed. When you look at density, actually structures starts appearing from the iron opacity region. And then line driving takes over at some point, and then you blow up. What about radial velocities? Well, below that, it's really 0. But at around the iron opacity bump, you start creating this inflowing, outflowing regions. But then something interesting also happens at around the photosphere, which you will actually notice later on when I show you means, is that there's a kind of a negative velocity. And then again, when line driving takes over, you just blow it away. So how else can we actually observe them? So let's imagine if I take one of this snapshot, and I take just one line of this, and if I plot it again in this weird scaling here, you might observe something like this. What if I take the whole thing? It's a mess. It's a bunch of these things, really, yeah. So a better way to plot this, and then you have a lot of time snapshots, right? So a better way to plot them would be to actually take a velocity space and your radius space and see where does things lie. Well, what do I mean by where does things lie? To check what is the probability of a certain cell to have a certain value. And that is done by this sort of plots called the probability density maps, where yellow is basically, there's a high likelihood of having that kind of value, and then blue is, less likely. And then the mean is all, in the plots that I will show you afterwards, the mean is always this reddish line. And then this is your, photosphere. And actually, there's a nice way to think about it, is that if I take a cut of this, it's a 2D histogram. Again, the colors are the same. So so in our work, we also, ran a grid of models, 3. If we can call that a grid, then. So what the grids was actually from a, the naming convention. Forgive me, spectroscopists, but it's not a spectroscopic naming convention. It's just, we looked at the effective temperature of our models, and we said, okay, this is kind of an O8 star. I don't even know what it means, but okay, so from top to bottom, you have your radial velocity, then you have your density, then you have your total gamma, and then you have your temperature or radiation temperature. So if I now populate this figure with the other models, the green line over there is your sonic point. The sonic point is where your wind starts outflowing, right? So, so now if you look at this gamma, you might notice that as we keep on moving to this high luminosity end, basically your base luminosity is already high. So at this iron opacity peak, gamma becomes greater than 1. Well, how I like to think about it, if your metallicity is similar to what the sun has, it's basically a factor of 3. So you increase it by a factor of 3 at the peak of the iron opacity bump. So this and this trend, what you notice is that if you look at your velocity, you might notice that as you start moving close to become more and more luminous, you keep on blowing the wind much closer to your surface of your star. So essentially, this star is becoming an Wolf-Rayet star, like So it's gonna, if you keep on increasing the luminosity, it's probably gonna drive a wind below the photosphere of the star. Whereas if you look at your density and your temperature structures, the dispersion in these quantities keeps on becoming more and more as you keep on increasing your base luminosity of your star. Okay, so now we have all these average quantities, the red things that you saw in these graphs, and we can calibrate our average 2D quantities to the 1D input that I have already shown you, and see if they match or not, right? So again, to remind you a bit, so we had our 1D structure, which is basically radiative envelope plus an analytical wind on top. Again, the photosphere is this vertical line. So what if I plot the average 2D structures on top of the 1D input structures? Well, your photosphere, shifts more inwards. So basically that means you have your envelope has expanded less in 2D compared to what is being observed in case of the 1D simulation. The implication of that is that your R star and your TEF basically changes. Also, this density inversion kind of thing actually washes away, and it becomes more like a density plateau. And also, the other thing is that the structure at around the photosphere it's quite different in the average 2D and 1D models. This might have quite a bit of implications, and I will come back to that later on. But for now, we want to let's investigate why. What is causing these differences, and how can we actually calibrate them to make them similar to our 2D models. So in order to do so, let's look at some average 2D quantities. So one of these quantities is your pressure terms. So basically, if you look at the top plot and at around the photosphere, you might notice that it's actually radiation pressure plus turbulent pressure dominated. The bottom plot is, so this is your dispersion in your radial velocity, and then it's V turb is basically the density weighted dispersion. So if you notice that these values are really high, and these values are actually reminiscent of this extra broadening macroturbulent velocities that we put in our 1D codes. But okay, this is one of the things that we probably might need to add to our 1D simulations. What else? What is the energy balance? So how much energy is actually transported in our 2D models via convection? Well, we find at some radii below the photosphere, it's 10%. What is that radius, or what is happening over there? Well, let's change the scale to temperature. Can anyone tell me what happens in this 200 to this 100,000 Kelvin? Anyone? Yeah, speak loud. Exactly. It's iron opacity peak. So 10% of your energy is actually transported via convection at the iron opacity peak region. So, okay, let's go ahead, and as I mentioned that your TEF changes and your R star changes, right? So we need to actually calibrate them, right, to something. Same R star, same TEF. Otherwise, we're comparing apples to oranges, right? But we need to compare apples to apples. This is, if your TEF changes, it's not the same star. So we calibrate them to have the 1D and the 2D model to have same R star and TEF. And now, what we do is that we add this turbulent pressure term, and we add a recipe of convection. Well, Jon did that, like a simplified MLT. And we do that to our 1D model, and voila. You have, quite a bit of agreement with how the average 2D looks. Well, the idea for us was not to actually exactly match, but to to spread the word to the community that we can do, that can be done and how it can be done, to point the way towards. So on to some further implications that we find in our models. So as you remember, I talked about the turbulent velocity, but I showed you just for one of these models. But what happens, what we observe in all the three models is the same trend. It starts somewhere around in the subsurface regions, like from like almost zero, and then it keeps on increasing to the photosphere of the star. And okay, so well, good. What are these values? So can we say something from that? So if we plot these values, like they actually, when you push towards this Eddington limit or you make your luminosity higher, you keep on increasing this these turbulent velocities. Well, this is quite well, 3 points, 1,000 points. But the idea is that okay, this looks what this microturbulent velocities has been added to added in 1D simulations. What about mass loss? Everyone wants to talk about mass loss, but we actually calculate mass loss from our models, right? So it's not an as input parameter as in 1D studies. So when we do so for these three stars, we find that it's quite an agreement to more focused theoretical studies. Björklund, another giant, and also observational studies as well. Clumping factor. We find in the outflowing regions it's in the range of 2 to 10. But again, it's a 2D simulation. So we usually have found, at least if you read Nico's paper, you will notice that clumping factors are much lower when you increase your spatial dimension. One thing we haven't taken into account is LDI. And well, we believe that LDI will increase the clumping factor in these outflowing regions, but it's difficult to implement, so let's see. So okay, all this brings to the point that what is next? What is next for a group? Or what is next for me? Well, Cassandra, you're again here. So Cassandra is actually gonna focus on these early stars, the population 3 stars. No metals at all. Well, she's going to focus to actually, see what kind of instabilities they have in this kind of stars. She's also probably going to do some of the simulations and see if you can have an outflow in this kind of stars. Well, this figure I borrowed from the master thesis of our previous master student. But yeah, this is the work that I think she's going to focus on. Peter recently joined our group, and he worked in his master thesis for the LVV stars, and it's also a nice simulation from his master thesis. So he's gonna work on the LVV stars. It will be an interesting project, honestly. So what about the other PhD that joined us? 2 weeks before, right? So Lara is going to take our O-star models. She's going to put it into line 3D and then generate spectra. No broadening terms. Well, the difficult part is actually installing line 3D. Olivier, okay. The senior PhD. So Olivier is going to actually, do a better calibration than we have done using O-star 3D models. So one of the things I also, if you notice, if you see, right, it's not well calibrated, right? If you also look at the energy balance in 1D, you actually have to send 20% via convection. compared to 2D, which is 10%. This can be solved by adding some sort of overshooting, because the peak is really, really sharp. Maybe a larger grid of models. But OK, we'll see about that. Well, I guess this is what I'm going to be doing next. One thing that is what we have done in our models is that basically are forcing an LTE condition. Basically, we assume that the flux Planck and the energy mean to be the same. And this is the heating and cooling term. So this basically forces your radiation and gas temperature to be the same. So we're moving towards approx NLTE. And well, I'm going to start working on that after my vacation. So what else? So the stochastic low frequency variability. And well, this is really something, yeah, we're not sure. I mean, many people argue upon what is the origin of this stochastic low frequency variability. So, well, it can be either from these waves originating from the core of the star. Well, astroseismologists know better about that. It can also be the subsurface convection as well. Or it can be both. Or you add the winds as well. So it can be all three of them together. So Nico and I are working on that. Let's see what goes on. Well, along with Cassandra, I also had a talk with Dominic as well, and Nadia as well. So yeah, OK. What else? Mass discrepancy. So what do I mean by mass discrepancy? So when you actually, for massive stars, when you calculate your mass from your spectra and use your evolution mass, they're not the same. Why? Well, your log G is different probably, right? You see these structures at the densities, for example, it's off, right? So this can be a direct implication of our multi-dimensional modeling. But again, we need to put some numbers on the paper and then to calculate what these differences would be. And finally, going back to MESA. Well, Connie already mentioned last week, right, that we need some dynamical boundary conditions for this 1D stellar evolution codes. Why? Because MESA extends until the photosphere, right? But you have noticed, right, how dynamic these regions are. So we cannot actually consider wind just as a force term. We need to actually rethink that, and we need to add this turbulent pressure and then wind in a more dynamical way. With that, well, I'd like to thank you all for listening. And
thank you, Dwaipayan. In the beginning of your talk, you mentioned that simulations look nicer than reality. Yeah? So I think the Plato team would agree with you here. So they would love to keep their simulations, never see the reality. Questions in the audience? Yup, we start with Pablo.
Hey, very nice talk. I already said it the other day. So I'm curious, in the plots you're showing the average velocity, it goes to negative values as well at some point. What about the average of density times radial velocity, which is essentially indicative of the mass loss rate across the shell?
Yeah, you're right. I don't have that plot here, but I will let you know, right, like what is happening. But again, so the thing with this negative velocity is that it's well, although you have this velocities of 50 kilometers per second or something like that, right? But then you have velocity dispersion in the order of hundreds, right? So can we observe that? Maybe not. So yeah, but we need to actually check the weighted velocities as well.
Okay, I'm curious in the sense of simulations reaching a steady state. And I would think that if a part of my model is really, there's a part that's outflowing and a part that's inflowing. So I would feel if that's the case, then your model is still relaxing to an equilibrium.
Well, I mean, I can show you. Yeah, they are actually relaxed because So this is one of the time snapshots of the models when we start. And well, I mean, so we take our averages much later than what I'm showing here, right? So we let them, so the wind dynamical times is 10,000 seconds in physical time, but then so it means that, and I start taking my averages 200,000 seconds after or something, so it means at least 20 times the wind has actually blown out. So the models should be relaxed by then.
But you also have radiative regions with radiative diffusion timescale.
Yes, so that's 1,000 seconds.
Huh?
That's 1,000 seconds.
Ah, that's faster?
Yes. 1,000 seconds and 10,000 seconds.
Okay.
Yeah, so that's a bit lower, right? So but then also, that also, it's 20,000 seconds, right? So if you think about it.
Okay,
yeah.
Thanks.
Hi, great talk first. But some of these questions might be pretty basic just because I'm not in stellar astrophysics, I do other stuff. But I'll go in reverse order. You mentioned LDI on one of your slides. What is that?
I don't know as well, but no, well, LDI is this thing called line driving instability. But if you ask me what is the reasoning behind that, I won't be able to do. You can ask Cassandra though. She's really into LDI. But you can read Florian's thesis, Florian Dessian from our group. His work is on LDI, so you can read up on his thesis.
Thank you. And then going further back, you mentioned that the iron opacity peak is higher than the other opacity peaks. Could you explain why that is? Just like
because, well, iron has a lot of iron, well, it has like 26 iron stages, right? And it has this millions of these lines, right? So, well, if you sum it all up, the effect is much stronger than what you expect. Even in case of wind, as for example, I can show a plot. I think I have. So even in the wind as well, if you think close to the photosphere, so actually the contribution from iron is much greater than any other well, groups of element. But yeah, because iron there's a lot of iron, and then iron interacts with the light in many different transitions. Yeah.
Sorry. Last question. You mentioned line-driven winds, but could you describe maybe what that means? Like, I understand winds and the whole concept, but what does line driving mean in terms of winds?
No, that's a good question. So basically, too many slides. So basically, think about it, your photon coming in, right? And then it interacts. It interacts with the line, right? And then it pushes. It supplies a little bit of momentum to your atom, right? And this is what I mean by line-driven wind. Alternative, you also have dust-driven winds. That's because of dust, but that's for cool stars, right? So that is the essential idea behind line-driven winds. But then you have this, well, increase because of this Doppler shifting mechanism. Okay.
Thanks. More questions? Yeah, yes.
Hey, Dwaipayan, great talk. So you showed the two plots of your V turbulent, which was one for your 3 points of, the grid that you talk about, and then the other plot where you have all the data points. And I noticed that the x-axes were not the same.
Oh, yeah, I know,
And that also, if I were to take, the 3 points at the top and put them at the bottom, they would not match at all with the data points. Is this just because my glasses are not,
your glasses are all right.
well calibrated?
No, so here this is the macroturbulent velocity, right? And this is just this density-weighted turbulence, right? So in order to actually, well, see what is going on, we need to calculate spectra, right?
Yeah.
And that's Lara is going to do that. Next year, maybe you see a plot where.
All right, I'll be here next year. Sadly. All right, thanks.
But the main thing is that the idea is the same. So the behavior is essentially the same.
Yeah, I thought you were kind of trying to compare visually, but no, I get that. Yeah, all right, thanks.
We have more questions. Joep?
So first of all, great presentation.
Thank you.
In the last part of your presentation, you talked about your future work.
Yeah.
So how does approximate NLTE radiative transfer compare to actual NLTE radiative transfer?
Compared to actual LTE radiative transfer. Ask me after my vacation. No. But it's so you separate out all this flux, Planck, and energy weighted mean, right? And so how we actually put in our LTE tables is that so if you see this is this force multiplier, and then we fit it with these three parameters. This is the Q bar, and then we have the Q naught, and then we have the alpha, which is the slope of this exponential part. And then this is calculated in the code based on what is the density and the temperature that is prevailing in the outflow. But then you separate out the flux, Planck, and the energy weighted mean, and then you probably have 3 of these tables multiplied by 3, so it's 9 tables, and then, well, then you read in again from the same depending on the same density, then in approx LTE, you separate out your gas and your radiation temperature, and you also have the dilution factor. So you then read out based on what's going on over there. But yeah, we need to see actually if we can actually fit like that. Well, Jon told me this morning that we can, but probably can be fit, and then we just supply the tables like we do for LTE tables as well.
Okay, it's just a table you fit.
Yeah.
Okay, thanks.
Any more questions? I'll have one. Dwaipayan, you mentioned the mass discrepancy. I think I hear about it for the first time. Could you elaborate a little bit on what you mean by that mass discrepancy, and what does it have to do with the surface gravity of the star?
Yeah. Okay. Yeah. So, so basically you fit your spectra, right? So you add some micro turbulence term to fit your spectra in 1D simulations, right? But then, so you have your spectra and you fit your spectra, and then you get your mass, right? Based on, well, whatever fitting parameters that you're using, right? And then you also calculate your evolutionary mass. But then the problem is that there is a difference when you do in those same 2 different methods, right? But in our case, what we believe is that we don't have to add these extra broadening terms, right? So we believe that these parameters that we're going to obtain, well, more or less might align to the masses that are, well, predicted by evolution or the other way around. But again, I haven't actually checked, but it's an implication that we think might come out of the simulations.
Mm-hmm. I think it might have to do with the fact if you include an extra term in your pressure, I think you're going to lower your gas pressure term a little bit.
Yeah, so the height scale is different, yeah.
And that might have some effect on the shape of your hydrogen lines. That is one of the main diagnostics for G
exactly. Yeah, your pressure height scales are different, right? So then, if you had,
And one more question: do you at all care about the cause of all those outflows? Because you've been talking about the line-driven outflows. Do you really care about the fact that it could be driven by, how can you would say, oscillations?
Well, if you, you have to, I guess. As long as you, we care about in the sense because there are certain parameters, right? So, as for example, if you read Robin's thesis, as for example, and if you have the massless prescriptions, which are off by factor of 3, you end up in the wrong side of the HR diagram when you evolve, right? So, you have to care about to get values, how, like as for example, mass flow rates or something like that. Yeah, so I think we have to care about, I don't know.
Yeah, thanks. Your last chance to ask a question. Oh, that's good, Alex. Take your chance.
Hi, Dwaipayan. Yes. Bit of a strange question, I guess. Like, so say in this plot, because it's a good one to talk in front of. So you've got your 2D, and that's essentially time meaned, right, at each point on the x-axis. So you're taking the time mean of your 2D simulation for the blue line?
Yes, time and radial mean, yeah.
So I'm just wondering, if you looked at, say, individual profiles, so not the time mean data, but like basically what your time meaning, do you find things that look like the 1D? Like, I guess what I'm wondering is, do things look like 1D, and maybe the reason things look so smooth is because your time meaning and all the noisy crap that is the turbulence in your 2D simulation is sort of washing it out?
Well, like if you take, this is just one of this, like literally one radial snapshot at one time, right? Well, does it look like 1D? I don't know, because I haven't compared, but well, it's difficult to say without actually seeing if it looks. But again, yeah, you're right. I mean, but it's an average structure that we're trying to calibrate to, right? Because, well, you are not resolving the parts of the star, right? So you're seeing an average effect, right? So that's what I mean by that.
Yeah. No, it seems like the right thing to do. It's just like your time meaning, and usually when you do these time means, especially with many, many elements, then yeah, things do tend to smooth. I'm just wondering if it's like, is it physics or is it just a procedural thing that you would inevitably get no matter what, I guess, but
yeah,
I don't know.
I won't be able to say without looking into them further.
Yeah. No, that's fine, I was just curious. Cheers.
Thanks, Alex. Any more questions? No? Let's thank Dwaipayan again then. Okay. Thank you. All right, I see a bunch of hungry faces, so enjoy your lunch and see you next week. A couple of colleagues have agreed to give your feedback on the presentation, so they will just bump into you.